Okay, so for this one, we're going to talk about two things that we did in Algebra 1 that we need to now take to the next step and do something with Algebra 2. I realize that a lot of you probably don't remember this from Algebra 1, or maybe your teacher didn't cover it, so we'll kind of review. So our first that we're going to talk about is completing the square. So completing the square is a process by which we force something to be a perfect square. So when we were looking at factoring before, if we had a perfect square, like say x plus 2 squared, and we multiplied that out, we would FOIL it. That would give us our x squared plus 4x plus 4. So in completing the square, what we're going to do is we're going to start with something similar to this, and we're actually going to force it so that we can factor it. So let's look at a couple of quick examples, and we'll talk about kind of the theory and then what we're going to do with it. So let's say we had something like x squared plus 6x plus 15. And we want to try to make this into a perfect square so that we can actually work with it. Our problem is that just looking at it, it doesn't work. We couldn't really factor this. Factors of 15 are 3 and 5, so we can't work with that. 15 and 1 doesn't work. So the idea behind completing the square is making it into something that's going to be a perfect square that can work. So what we have to do is we have to add something and then either take it away on the same side or add it to the other side to force it into that square. So let's go through the process on this one here. If I had a number, I could add something here so that this part just right here, not including the 15, would make this a perfect square trinomial. To do that, what I'm going to do is I'm going to take this middle term, 6, I'm going to divide it by 2, and then square that result. And that gives me 9. This is the number that I need to add to make it a perfect square. So taking our x squared plus 6x, if it was plus 9, this would now be a perfect square. We could actually factor it and we'd get x plus 3 squared. Notice that this number right here is the same as this number when we calculate it. So that's our basic idea. Working with it, we have a little bit more tricks that we have to do though, because we can't just add any number we want. So we have various ways to work around it. So I'm going to show you a couple examples of what we'd actually do with this, and then graphically kind of how it works, and then we'll finally talk about what we need to do with it for Algebra 2. So let's take just a quick example. So let's say we had x squared plus 10x plus 8 equals 0. And we needed to solve this or work with it, whatever it might be. In Algebra 1, they should have had you do completing the square in order to solve via roots, like what we did in our last lesson. So let's say we wanted to work with that. What I'm going to do is I'm going to take the x squared and the 10x, because that's part of what we need. And I'm just going to ignore the 8, honestly, because it's just kind of messing with us. So I kind of leave a gap. The process for completing the square is we take that middle number, whatever is in front of the x, and we divide it by 2. So 10 divided by 2 gives me 5. This we square. 5 squared is 25. This is the number now that we can add in to make it a perfect square. So I'm going to add 25 to both sides of the equation. Doing so now gives me x squared plus 10x plus 25. There's our perfect square. Plus 8 equals 25. This part right here is now a perfect factoring square. We can actually break it up, and it works out, if we factor it, to be exactly that number in both. So we have x plus 5 squared plus 8 equals 25. So we've done completing the square. We forced it into a perfect square. In Algebra 1, what they would have had you do next is move the 8 over, and then we can solve by square roots, similar to what we talked about in our last lesson. Just so you can kind of see what that looked like, we could subtract 8. As an example, that'd give us x plus 5 squared equals 17. And then we can go through our solving process like we did in the last lesson. We would take square roots, get our x plus 5 equals plus or minus root 17, and then we could subtract 5. This is not what we're doing here. This is just what they would have had you do in Algebra 1. So that's kind of what we did before with completing the square. What we need to do now, though, as we use this same process, is convert equations into it, where it's not equal to 0, but we just have something else. So let's take our equation y equals x squared plus 8x. If I want to use completing the square on this, then I can. So we take a look and we say, okay, there's no number in front of the x squared. We just have that 8. I'm going to take the 8 and divide it by 2, and that gives me 4. I square that, and I get 16. So 16 is the number that we would need to add in to do completing the square. So I add 16 to both sides. And now I can force it to factor. So I get y plus 16 equals, and this becomes x plus 4 squared. I can subtract this 16 back over, so we can go back into y equals. I have y equals x plus 4 squared minus 16. This is what our goal is. What we are going to use completing the square to do is to transform an equation from standard form into vertex form. There's a lot of things that vertex form is actually really useful for that we don't necessarily want to try to graph and find. So what we can do is we can actually force something into vertex form using completing the square. Again, that process is we always take the middle number, we divide it by 2, we square it. That's what we need to add to both sides. This was completing the square from Algebra 1. Let's do another one, only full directions this time. So let's convert y equals x squared plus 6x into vertex format. Let's make it a little bit harder. Let's say plus 10. And we want to convert this into vertex format. So again, what we're going to do is we're going to take that middle number, 6, I divide it by 2, and that gives me 3. I square that 3, and I get 9. So we would need to add 9 to both sides to force this into vertex format. So y plus 9 equals x squared plus 6x plus 9. And then we still have that plus 10 that we kind of ignore because I don't want to deal with them. This part is now a perfect square where that 3 that we got is what's going to be in it when we factor it. So I get y plus 9 equals x plus 3 squared plus 10. Finally, I can subtract that 9 off. I get y equals x plus 3 squared plus 1. This now is in vertex format. We can see the vertex is negative 3, 1, and then we could work from there. This is the part that we need to do from Algebra 2. We're going to use completing the square to force something into vertex format. Let's do one more kind of basic example like this, and then we'll take a look at what it could look like if they're a little bit harder. So again, our directions are to convert it into vertex format. So put into vertex format. Y equals x squared plus 4x plus 19. Okay, so we need it in vertex format. We have it in some kind of standardized format or something else. It honestly doesn't matter what we start with, but we want to end up with vertex format. So I need this to be a perfect square. I'm going to ignore the 19 and just kind of draw it out with a gap. So I need to decide what number we could add so that this thing becomes a perfect square. So again, I take that middle number of 4, I divide it by 2, and I get 2. I square that, and that equals 4. So 4 is the number that we need to add to both sides. So I add 4 on both locations. This is now a perfect square, so I can factor it, and it's going to be x plus whatever we got right here squared, x plus 2 squared. Final step, we remove the number from in front of the y, and we get y equals x plus 2 squared plus 15. So again, we've converted it from standard form into vertex form. All right, so what if the lead coefficient's not a 1 though? Because that makes things a little bit tougher. So let's look at the harder example then. What if we started with y equals 2x squared plus 6x plus 8? Now, I don't know, let's make it even worse. So we can't just factor out the 2, plus 9. Okay, so if we have a leading coefficient, it makes our job a little bit harder, and this is where we have to be a little more careful. What I'm going to do is I'm still going to write it out. We still have to add something to both sides, so we still need that gap where we can add it. So we're going to have y plus something equals, and then we still have our plus 9. To work with this, our perfect square only works if we're taking half of the right value. So we have to factor out whatever this leading coefficient is. If I factor that leading 2 out of these two terms, I'm left with x squared plus 3. So that'd be x squared plus 3x, and then we still have our plus 9. We need to add something right here to make it a perfect square. So this is where I'm going to add a number here. So I take this value, because we still have our x squared, there's our b, and I divide it by 2. 3 divided by 2 is just 3/2, and then I square it, and I get 9/4. 9/4 would be the number I need to add. So I add 9/4. Now we can't just add 9/4 on this side. While I put a 9/4 right here, so that this thing will be a perfect square, problem is that we actually added more than just 9/4. If we were to multiply this back out with the 2, we'd have to distribute it. We'd actually get 9/2, because 2 times 9/4 is 9/2. So I really added 9/2 to both sides. So I need to put the 9/2 here to match it. This is now factorable, so I have y plus 9/2 is equal to 2 times, this is a perfect square trinomial whose middle term is this, x plus 3/2 squared, and then we still have our plus 9 coming along for the ride. Final step, I need to solve for y, so I'd subtract 9/2 from both sides. That gives me y equals 2 times x plus 3/2 squared plus 9 minus 9/2 is 9/2. So this would be our equation in vertex form. I'm going to do a couple more of these so you can see this process again when we have a leading coefficient, because that's a little bit tougher than it was usually in Algebra 1. So let's do another example. Y equals 3x squared let's make one 3x squared plus 18x plus 5. All right, so again, we're taking standard form. We need to write it into vertex form. So I'm going to rewrite it with some nice gaps, leaving us room to work. Here, again, we need to have only a 1 coefficient, so we have to factor out that 3. If I factor out that 3 from just those two terms, that leaves me with x squared plus 6x. For a perfect square, we need to now decide what number we're going to add right there. So I take that middle term of 6, and I divide it by 2. That gives me a 3. I square it, and I get 9. So I would need to add a 9 to make it a perfect square trinomial. But if I put a 9 right here, I've really added 27 to this side of the equation. The 3 times the 9 when we distribute would be a 27. So I need to add 27 on this side as well to balance it. Now we can factor this. So I have y plus 27 equals 3 times. This is now a perfect factored trinomial with that as my term, x plus 3 squared. And we still have our 5 bringing along. And finally, we can solve for y by subtracting what we added. So if I subtract 27 from both sides, I get y equals 3 times x plus 3 squared minus 22. This now is in vertex format. So going over the process again from start to finish. When we use completing the square, we need to identify the b value. We need to identify that second term. Once we know what that second term is on the trinomial, we divide it by 2 and square it. That tells us what number we need to add to both sides to make this work. If the leading coefficient is 1, then that's all we need to do is add the number to both sides. If we had to factor out something, then effectively we're really adding not just this number, but this times the distributing. So that would tell us what we'd have to add. In this case, when we did it, we factored out a 3, leaving us with x squared plus 6x. 6 is the number now that we divide by 2. We got 3. 3 squared was 9, so we'd have to add an extra 9. If we put a 9 right here on this side of the equation, that's really adding 27 to this whole side, because 3 times the 9 is the 27. So I have to add a 27 to this side of the equation to still balance it. Then we can factor it. This is now a perfect square trinomial where this 3 is the number that goes in for factoring. And we can finally solve for y. We've now converted this standard form equation into vertex form. So that's what we're working with. We're working with completing the square from Algebra 1. We're using it in a slightly new way. It's still the same completing the square that you did before. All right, our second topic is something people usually do remember a little bit better. And that is the quadratic formula. So just as a reminder, the quadratic formula is something we can use to solve any generic quadratic. So this was our standard form equation for a quadratic equation. It is completely generic. We don't know any values. However, we learned in Algebra 1 that we have one particular formula that can solve this, and that is the quadratic formula. So what the quadratic formula said was, given this, and we have the whole thing equal to 0, we can actually solve for x, as I write a squared for some reason. Ax squared plus bx plus c. So now that we actually have it equal to 0, we can actually use the quadratic formula. Quadratic formula said that if this was a quadratic term equal to 0, that x would be equal to negative b plus or minus the square root b squared minus 4ac, all divided by 2a. Usually in Algebra 1, they'll often make you memorize it to a psalm. The traditional one was usually Pop Goes the Weasel or Twinkle Twinkle Little Star. I've personally found Wrecking Ball to be the most amusing and probably the best fit, but whatever will help you remember it. However they made you remember it in Algebra 1, you still need to remember and use it here. The only difference from what we're doing now compared to Algebra 1 is now we can get complex answers. We can actually solve things. So let's kind of review what that looks like when we have a process. So let's say, we'll start off simple. We have x squared plus 2x plus 1 equals 0. Now this is a nice, easy equation. We could actually factor it and get our answers via factoring. We could use completing the square to force it into a square root solver. That would be fine as well. But let's do this nice, easy one in terms of the quadratic formula first before we look at some more. So our quadratic formula says that we have ax squared plus bx plus c equals 0. So my a in this case is 1, my b is 2, and my c is 1. So now I can plug all those into the quadratic equation. So I have x equals, negative b would be a negative 2, plus or minus square root b squared, so that's 2 squared, minus 4 times my a of 1, times my c of 1 all over 2 times my a of 1. So all I've done is I've plugged in each of those points. Now we can start simplifying it. So that's negative 2 plus or minus the square root of, oh, that gives us 4 minus 4 over 2, which gives me negative 2 plus or minus the square root of 0 over 2. Square root of 0 is just 0. So that gives me negative 2 over 2 is just negative 1. So we get one answer. Now this corresponds to what you should have talked about in Algebra 1 for the quadratic formula. If we think back to graphing, we have different ways we can get a different number of answers. It could come up and just touch, which is the case we have here, where the graph just barely touches the x-axis, and we get one single solution. We could have the graph pass through the axis twice. This is where we get two equations, or two answers, I should say. And matching kind of what we talked about in our previous class with complex numbers, we can actually have the graph come and never touch, either above or below. And this is what gives us our complex numbers with I. So let's look at that a little more detailed. So again, if we have our y equals ax squared plus bx plus c, and we're solving this for 0, when we plug that into the quadratic formula, we get our x equals negative b plus or minus square root b squared minus 4ac all over 2a. Now what happens with this root is really what determines what happens to the whole type of answer. So we actually call that b squared minus 4ac the discriminant. Let's see if I can actually spell it today. Because it discriminates between how many different answers we can get. In our previous problem, when we did our b squared minus 4ac, we got 0. And that actually gave us one answer. If our b squared minus 4ac is positive, so it's greater than 0, then we're going to get two real answers. We're going to get actual numbers. We can take the square roots. They might be decimals. They might be a reduced root, whatever. But we'll get two actual real answers. If we did our b squared minus 4ac and we got less than 0, we get a negative. Well, that means we'd be taking the root of a negative, so we're going to end up getting two complex answers. We're going to have i's. So this is kind of why it's called the discriminant. It actually discriminates between the different answers. It tells us what's going to happen with the problem. So let's do another one. Let's actually solve with the quadratic formula. So how about y equals 2x squared plus 4x plus 5. All right, so we have y equals 2x squared plus 4x plus 5, and we're going to solve it for 0. So we identify our a, b, and c first. Remember, it's ax squared plus bx plus c. So my a is 2, my b is 4, and my c is 5. Now that we know the coefficients, we can actually plug it in and solve. So I get x equals negative my b value of 4 plus or minus the square root of b squared minus 4 times our a is 2 times our c is 5 all over 2 times a. So we've plugged in all of our useful information into it. Now we just need to simplify. So that gives me negative 4 plus or minus the square root of 4 squared is 16. See, 4 times 2 is 8 times 5 is 40, so 16 minus 40 all over 4. Okay, we keep going. So that's negative 4 plus or minus the square root. 16 minus 40 is negative 24 over 4. And negative 24 is exactly what we were working on last time in terms of complex numbers. So again, the negative just means we're going to have an I, and then we would reduce the 24. So I know I have an I because it's negative. Reducing 24, well, let's see, that's square root of 4 times square root of 6. So that's 2 root 6. So square root of negative 24, as we practiced in our last example, is 2i root 6. So I get negative 4 plus or minus 2i root 6 over 4. And then this is pretty good, but a 2 can go into everything. So I can factor out and reduce it by a 2. So I get negative 2 plus or minus I root 6 over 2. This is acceptable. If they wanted you to write out actually the two answers separate, we would just write it out separately. You could also, if you don't like the fraction like this, we can split it up. So remember, if we're dividing everything by 2, it goes into everything. So that would be negative 1 plus or minus 1/2 I root 6. Because 2 over 2 is 1. I over 2 is just 1/2 I. You can write it either like this or like this. I don't care. Either one is perfectly valid for me. So that would give us our two solutions. In this case, our discriminant was negative 24. So we got two complex solutions. All right, so let's do another one. So again, solve. Negative 3x squared plus 2x minus 10. Okay, so we have our new quadratic. We need to solve it. So I'm going to identify my A, B, and my C. Again, it's A. I keep writing Y today. It is ax squared plus bx plus c equals 0. So my A is negative 3. My B is 2. My C is negative 10. And I'm going to get some bigger numbers this time. So I go to my formula. X is equal to negative b plus or minus square root b squared. So that's 2 squared minus 4 times a, which is a negative 3, times c, which is a negative 10. And be careful here. This is the common point where we see a lot of errors, is just tracking all the negatives. All over 2a, 2 times negative 3. So again, it's negative my b value plus or minus b squared minus 4 times my a is negative 3, my c is negative 10, all over 2 times a. So let's start simplifying that. So that's negative 2 plus or minus the square root of 4. Now let's see. 4, well, negative, 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 so it's going to be a negative. 30, 120. So we get minus 120 over negative 6. It's negative 2 plus or minus the square root of 4 minus 120 is negative 116 over negative 6. All right, so let's go off to the side and figure out what root negative 116 is. Again, that negative just means I'm going to have an I in it. So I need to break down 116. I know that's a big number. I don't know if anything nice goes into it. But so I'm going to use my prime factorization. So that would be 2 times 58. See, that would be 2 times 29. 29 is prime. But that gives me 2 2s, so I can have 2 root 29. Yeah, so at least it can reduce a little bit. So when we come back over here to continue simplifying, it's negative 2 plus or minus, and we've established that root negative 116 is plus or minus 2i root 29 over negative 6. Again, there's a 2 in all three parts, so we can reduce the fraction. So that would give me negative 1 plus or minus I root 29 over negative 3. If we wanted to write out the complex number in standard form, I could actually distribute it to both, giving me 1/3 plus or minus 1/3 I root 29. So this is using the quadratic formula, which is what you did in Algebra 1, but with the difference being now we can actually get complex numbers that include I as our answers. So it's the same exact process we did before, just combined with what we talked about in the last class, where we can have I when we take square roots of negatives.